In the last class, we discussed about simply supported two-way slab design. Okay, so while designing two-way slab, you know what is two-way slab is? There are two types: simply supported two-way slabs, in which the slabs can be like this after bending. Okay, if this was the support, this is the support, slabs are susceptible to bend like this. Okay, these four corners can go upwards because it is simply supported. The design of this simply supported two-way slab we discussed about in the last video. So today we are going to discuss about restrained two-way slab. Restrained two-way slab is, the difference is this upheaval or upward movement is not allowed. The movement is restrained or restricted. That means the corners will be held down. Okay, so whatever load may act on this slab, the slab will be holding its positions on four corners. Okay, so that is the primary idea of restrained two-way slab. So we are moving on to the theory part of restrained two-way slabs. Okay, suppose this is a restrained two-way slab. It is a single restrained two-way slab. Okay, this is the case. In this case also we have Lx as shorter span and Ly as longer span. Okay, so in this case, if this rectangle is the plan of this slab, single slab, okay, we will be designing on the basis of torsion reinforcements. We will be designing normal AST reinforcements with a certain criteria. We will be getting into that. In addition to that, we will be designing torsion reinforcements at four corners for perfect bonding of this slab into the support systems or columns in that sense. Okay, so simply supported two-way slabs were mostly about masonry structures. Our homes, mainly one-story buildings, two-story homes or residential buildings, etc., are made usually on simply supported basis. The slabs are rested upon on a masonry work. There is no bonding. Okay, their corners are susceptible to move upwards while loading. But in case of multi-story building or flats or any multi-story building, we will be building on framed structures. Like first we will be building columns, then beams, then over that we will be building slabs before masonry structures. After that we will be filling with bricks, right? So in flats and multi-story buildings, frame structures are used. In these frame structures, the ends will be restrained. These columns, beams and slabs will be all monolithic because all will be RCC, right? So it will be a restrained condition. There will be bonding between the corners, with the corners and supports and the slab. Okay, so that is the real life application. And in case of further classification, this is a single one. You can classify this. You should be understanding these corners need to have torsion reinforcements. All these four corners to make this slab endure the torsional force arised from this upheaval. We are not allowing the slab to move upwards, so we need to provide torsion reinforcements. Okay, so this is the simplest form, and this one is primarily called as four edge discontinuous slab. Okay, this is just a single slab. There is no continuation of slabs in any of the directions. So that means 4-edge discontinuous slab. All the 4 edges are discontinuous. Okay, so if we take another example, suppose a similar slab like this, but in addition to this portion it is a bigger one like this, but there is beams running through in between. Okay, so this area will be approximately, this single area will be approximately equal to this area, suppose. Okay, so we have 4 slabs with supports. These are the supports. Okay, so in this case this was 4-edge discontinuous slab. In this case, how many edges are discontinuous? 1, 2. Okay, so all these are, this slab is having 2 edges discontinuous. The rest of the 2 edges have continuous like this, continuing for the next slab. If considering this slab, this edge is continuing this to the next slab, and this edge is also continuing to the next slab. Okay, so all these 4 slabs can be named as 2-edge discontinuous slabs, right? Okay, I hope it's clear. And in the next level, if suppose there are 9 slabs like this. These lines are beams and these lines are columns. Okay, so this is 2-edge discontinuous slab. This is what? This edge is continuous, this edge is continuous, this edge is also continuous. So 1-edge discontinuous slab, right? This is 2-edge discontinuous slab, this is 1-edge discontinuous slab, likewise, and this will be called as intermediate slab. That is, there won't be any discontinuity, no discontinuity. All the edges will be continuous. 4 the edges are continuing. Okay, so this is intermediate slab, this is 1-edge continuous slab, these 4 slabs. These 4 slabs are 2-edge discontinuous slabs. Okay, so that is the naming. So the relevance of this naming is you should be able to follow the naming on the IS code also. So the IS code will be giving some values with respect to these namings. Okay, intermediate, 2-edge discontinuous, 1-edge discontinuous, 4-edge discontinuous, etc. Okay, sometimes 3-edge discontinuous can also come into being. Okay, so this is the scenario. Okay, so simply saying, if we are considering only a singular slab, this is 4-edge discontinuous slab. Back to the basics. Okay, so while designing 4-edge discontinuous slab, what is the difference between restrained and simply supported? What are the difference should be made in 2-edge slabs? It is very simple. While designing of a 4-way, same thing I am drawing here, same thing, LX, LY. Okay, in here we will be designing not the reinforcement, not for the whole slab, we will be designing reinforcement dividing this slab into strips, edge strips. Okay, so I'll make you understand. This LX, this is the shorter span, right? LX direction is the shorter span. So this direction will be divided into two lengths, two edges like this. 3 strips for exact. Okay, so one strip, second strip, middle strip and third strip. 2 edge strips and 1 middle strips. Okay, and this length will be such that 3 by 4 LX is will be the width of middle strip. Middle strip. I think I don't need to write the name of middle strip. This is the middle strip. The width will be 3 by 4, 75% of total shorter length, shorter span. 3 by 4 LX. Okay. So then these two will be equally distributed. While be equally distributed, the remaining will be 1 by 4. So again half of these two are 1 by 8 LX and again 1 by 8 LX, obviously. Okay, the central 3 by 4 LX is called middle strips and the remaining 1 by 8 LX and 1 by 8 LX, you will get it as edge strips. So obviously 3 by 4 plus 1 by 8 plus 1 by 8, you will get 1. Obviously. So in this side also, LY side also, we will be designing reinforcements on the basis of 3 strips, same criteria. It will be like this. This is the middle strip with respect to longer span. LX, sorry. Three by 4 LY, same thing. 1 by 8 LY, 1 by 8 LY. Okay. I hope it's clear. This is how we are going to design the reinforcement. Okay. The criteria is along the mid strip only we will be designing. With respect to that table we had done a simply supported 2 slab. Only the middle portion or middle strip we will be designing. The edge strip will always be minimum reinforcement. We know what is minimum reinforcement. For HYSD slab, for HYSD steel, minimum reinforcement is 0.12% BD. Right, that is the minimum reinforcement. We will be in all the directions. We will be giving reinforcement the end strip as minimum reinforcement, and for middle strip you will be giving AST. Okay, so in this direction you will be giving AST Y, and in this direction you will be giving AST X, as we designed in one-way slab. Okay, we will be selecting values from a different table. That's the only difference. Okay, so that is the concept. I hope it's clear. This is a restrained 2 slab, and for this we call it as 4H discontinuous slab. Okay, and we have to provide torsion reinforcement. Details about torsion reinforcement will be discussed later. Okay, and for designing of restrained 2 slab, we need to divide into 3 strips on both direction, LX direction, LY direction, with middle strip as 3 by 4 LY and 3 by 4 LX, and edge strips are 1 by 8 LY and 1 by 8 LX on both sides. Okay, so in edge direction we will be giving only the minimum reinforcement along the edge strip. In the middle strip, 2 directions of middle strip, we will be giving AST values that we calculate on the basis of tables in IS 456. Okay, so we move on to problem. So this is the question. You have the information all here. In this question, it is stated that to design a simply supported slab. Okay, and dimension is given. Inner dimension is given. Embossed load is given. M20 and Fe415 steel is given. Slab is supported on all edges and corners are held down. Okay, so even if they are stated that it is a simply supported slab, this information changes our criteria. Corners are held down. That means it is a restrained slab. It is not just a simply supported slab, it is a restrained slab. All corners are held down. Okay, so it makes a restrained two-way slab. You will be designing in a new way. Okay, so we have the dimensions here. So I will just draw this 4 meters. This is Ly, that is 5 meters. Longer span. Lx, that is 4 meters. Okay. So we will just start. Obviously the first step is we want to design if it is a two-way slab or one-way slab. So how do we do it? Lx by Ly by Lx. Ly is 5, Lx is 4, is 1.25, that is less than 2, that is two-way slab is to be designed. Okay, so it is less than 2, Ly by Lx is less than 2, so two-way slab is to be designed. This slab is a two-way slab. Okay, so now we are going to design the overall depth as always. This L by D. In here it will be Lx by D, and as we did in the simply supported slab, this 35 will be obtained from the IS code for two-way slabs for simply supported, and into 0.8 is when we have a HYSD steel used. We are using Fe415, so 0.8, that is 28. We have Lx as 4, we will get D as 142.8 mm. We will approximate as 150 mm depth slab. Okay, so we have D as D is equal to 150 mm. Okay, so you need to calculate dx and dy the same way. Dx is 150 minus 20. Obviously Lx you will be having clear cover minus only the half of reinforcement, main reinforcement along Lx direction, that is, if suppose we are assuming it as 8 by 2, that is 126, right, 126, and dy 150 minus 20 minus this reinforcement 8 minus 8 by 2, that is 118 mm. So you have, and you will be using main value as, you will be using both, but dx will be 126, dy will be 180 mm. Okay, so now you will calculate effective span. Effective span, you have two ways to calculate. One way is clear span, that is Lx plus D. In this case it is dx, That is equal to 4 plus 0.126. 0.126 in meters. That is 4.126 meter. Second way is center to center supports. If suppose we are assuming it as a 300 mm dimension support of RCC column, we did assumed 300 in the last video also. Okay, so Lx plus 300 by 2 plus 300 by 2, you will get it as 4.3 meters. So least of these two will be selected as effective span. So 4.126. So Lx is equal to 4.126 meters. Although here at present Lx is here, in all the next calculation we will be substituting this value as 4.126. Okay. Next, the load calculations. So the same load calculation is done by dead load is equal to 25 into depth is 0.15, breadth is always 1, then it will be 3.75 kilonewton per meter. Live load will be equal to floor finish load plus imposed load. Okay, so floor finish load is usually assumed as 1 kilonewton per m square plus given imposed load is 8 kilonewton per meter square. Okay, so you will get it as per meter as 9 kilonewton per meter. When you multiply it with B 1000 mm, 1 meter, obviously. Okay, so adding all this dead load and live load, total load will be equal to 3.75 plus 9, that is 12.75 kilonewton per meter. To get factored load, we multiplied with obviously 1.5. 1.5 into 12.75, you will get 19.125 kilonewton per meter. This is the factored load. So we have W as 19.125 kilonewton per meter. Now you calculate bending moment. For bending moment, we will calculate on Lx direction and Ly direction, and instead of using page number 91, table 27, you will be using table 26 from same page. The equations are the same. Mx will be equal to alpha x w Lx square. My will be equal to alpha y w Lx square. Okay, but you will be calculating alpha x and alpha y from table 26. Okay, so as we said earlier, this is as there is no other slabs around it, it is a 4 edge discontinuous slab. Okay, so as this is a 4 edge discontinuous slab, we will be taking values from the bottommost row, that is the 9th one from page table 26. Okay, so you will get values with respect to Ly by Lx ratio, that is 1.25, 5 by 4. Okay, so the corresponding values for 1.25 you will have to interpolate from this value. As it is 1.25, you will be having 1.2 values and 1.3 values. So it is easier now, you can just take the average. But if not, this value is different, you need to interpolate the value from those two values. Okay, so the alpha x value is 0.0755, alpha y value is 0.056. Okay, so based on these values, W is 19.125, Lx is 4.126. Okay, so Mx you will get it as 24.42 kilonewton meter. My you will get it as 18.23 kilonewton meter. Okay, so you have Mx and My values. Now you compare it with Mx limit and My limit values. The equation is simple as it is. Fe415 0.138 FCK B dx square, this value 0.126 mm. Okay, so we all know what rest of the values. In this it will be 0.138 FCK B dy square. Dy will be 118. Okay, so you will get Mx limit as 43.82 kilonewton meter and My limit as 39.8 something. Okay, so obviously these two values are greater than corresponding Mx values, moment values, Mux and Muy, or Mx or My. Okay, so it is safe and these are under reinforced, so you can continue with the given values. Okay, so now you calculate AST. For calculating ASTx, you will get the equation, same old equation, 595 mm square. ASTy is equal to 466 mm square. Okay, so you have these two values. These values are important. Okay, so the next step is check for minimum reinforcement. Right, so check for minimum reinforcement is minimum AST is equal to 0.12 B into D. B is 1000 and D is 150. You will get it as 180 mm square. Okay, so we will check with these two values. Obviously far off, obviously these values are safe over the minimum value. So the next thing is spacing. Spacing is equal to 1000 A5 by ASTx, that is 1000, we are assuming 8 mm diabars. 5 by 4 into 8 square divided by 595. You will get 84.4 something mm as spacing. You will take it as 80 mm spacing. Okay, so in here spacing 1000 into 5 by 4 into 8 square divided by 466, you will get 107 mm, around 107 mm. So we will approximate 105 or 100 mm spacing. Okay, now you should check these values with maximum spacing. Maximum spacing is 3D or 300. Right, so 3D will be in any way over than 300. So these two values are lesser than maximum values. Okay, so this will be safe. It should be written as a step. I am not writing it as a separate step. Okay, so you have the reinforcement in x direction. In this direction, Lx direction is 8 mm dia bars at 80 mm center to center spacing. Okay, so in this direction, Ly direction, it is 8 mm dia bars with 100 mm spacing center to center. Okay, so we have the main diameters, main AST values. Okay, moving on. So you have ASTX and ASTY values for reinforcement. We have the diagram. Okay, so we'll start drawing the diagram. Okay, or the representations of reinforcements here. So as we know, we said there will be a middle strip on each directions and two end strips, right? So middle strips will be in this direction, Lx, Ly direction will be like this. Okay, so ASTX 8 mm dia bars at 80 mm center to center spacing will be laid like this. Okay, from this point to this point. Okay, understand? So this will be 8 mm dia at 80 mm spacing. Okay, so from this point to this point along the middle portion, what will be the dimension of this? 5 into 3 by 4, that will be 3.75 meters. This dimension will be 3.75 meters, right? So this value of reinforcements will be provided along Lx for this much distance, 3.75 meters. I hope it's clear. And what will be ASTY along Ly direction, 8 millimeters, 8 mm dia bars at 100 mm centered spacing. It will be provided along the midspan in this direction. Okay, this will be the midspan, and this dimension will be 4 into 3 by 4, 75% of Lx, that is 3 meter. 3 meter will be this dimension, and obviously it will be provided like this. Okay. It will be 8 mm dia at 100 mm space, that is ASTY. So we have filled reinforcement from this point to this point as this value, and this point to this point as this particular value. So what will be the rest? What will be the reinforcement in this directions, this area? Minimum reinforcement. Minimum reinforcement, we calculate it as 0.12% of B into D, that was 180 mm square. So we have AST for these all areas, 4 strips, right? So we need to calculate spacing. Spacing is equal to 1000 into pi by 4 into 8 square divided by 180. That is 279.3 mm. Okay, so checking for maximum spacing in distribution. This is a distribution reinforcement, right, in all four edges. So maximum spacing is 5D or 450, right? So obviously if you check it, D is always greater than dy or dx, whether it is dy or dx, it is greater than 100. So this will be the lesser value, and obviously it is greater than the calculated spacing. So we adopt all these four areas as 8 mm dia bars at 270 mm center to center spacing. Okay, so this will be provided along this direction. So we will mark it as X. Okay, and also this direction, and in here and in here also. Okay, so figure will be a little complex, so try to make it more neater. Okay, when you finish it. And now we have to add torsional reinforcement in here also. Okay, so this is the reinforcement without torsion till now. Okay, so now we are going into torsion reinforcement. So while calculating torsion reinforcement, you need to know a little bit more. Okay, so as we said earlier, this restrained slabs can be of various types: 4-edge discontinuous, 3-edge discontinuous, 2-edge, intermediate slab, etc. Okay, 1-edge discontinuous, etc. So for each types of slabs, there can be 3 types of supports or corners. Okay, so they are C1, C2, C3. Okay, so please be attentive. So in this, suppose, as I said earlier, we spoke about it earlier. In a slab system like this, with this being intermediate slab, this being 2-edge discontinuous, and this being, so this being 1-edge discontinuous, and this being 2-edge discontinuous slabs. Okay, so you have that picture. This is a plan of 9 set of slabs supported beam. These are the beams. This is plan. I am not expressing the isometric view or anything. Okay, so there is columns underneath. So in this set you will be having various types of corners. For example, this one, this is C1, that is discontinuous in 2 edges. It is not with respect to slabs, it is just with respect to this corner point, this corner only. When you consider this corner only, it can be, it is just discontinuous in 2 edges, this edge and this edge. Okay, so discontinuous in 2 edges, that is C1. Okay, then you have C2. It is discontinuous in only 1 edge, right? You have continuity in this bare edge, this edge and this edge. Only there is discontinuity in 1 edge, right? So for this corner, do not confuse it with slabs. We are talking about corners here, C1, C2, C3. There are 3 types of corners. C2 is discontinuous in 1 edge, that is C2. The last one, C3, is C3. This is C3 being continuous. There is no discontinuity, right? Okay, so all four edges are continuous. So this is 3. Okay, so for each of these corners you can express either of these 3. Okay, for example, this will be C3, this corner will be C3, this will be C3. Okay, simple as that. Which all will be C1, discontinuous in 2 edges. C1 will be this C1, C1 and C1, right? And C2 will be more numbers. This C2, 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 okay, so that is the idea. That is only 3 types. You cannot find more than that. C1, C2, C3. C1 is discontinuous at 2 edges, that will be at the corners without discontinuity. C2 is at the edge, 1 edge discontinuity at the edge, and C3 is no discontinuity, continuous. Okay, so in any case we will be having a torsional reinforcement, and torsional reinforcement will always be torsional reinforcement will be equal to, always in any case torsional reinforcement will be equal to 3/4 into shorter span AST. Shorter span AST, that means ASTX, the maximum value. Okay, so 3/4 ASTX. This will be torsion reinforcement. Okay, so this should be calculated in any case, and the difference is if we are considering a corner as C3, you don't need torsion reinforcement. No torsion reinforcement. Okay, because there is continuity all around. You don't need to give any torsion reinforcement. C1 you need to give complete value, that is 3/4 ASTX, that is full torsion reinforcement. Okay, for C2, as it is having one more continuous edge compared to C1, you need to provide only half torsion reinforcement, that is 1/2 into 3/4 ASTX. I hope it's clear. So this is the idea. You can calculate the torsion reinforcement beforehand as 3/4 AST. If the corners, you should calculate the corners accordingly, and C3, if there is a type C3 corner, you need not provide any reinforcement for torsion at the corner. If it is C1, you need to provide full torsion reinforcement. If it is C2, you need to provide half torsion reinforcement, half of this value. Okay, that is the idea. In our case, this is the full theory of torsion reinforcement, that's it. Okay, so in our case, the slab is slab is 4 edge discontinuous, right? There is no continuation. We have restrained the corners, but the slab is 4 edge discontinuous, right? So what will be the type of corners? Will it be C1, C2 or C3? It all will be C1. because there is no supporting slab, so continuous slabs. In any case, C1 will be the reinforcement. Okay, so in that case, in this question we don't need these portions, we just need to give full torsion reinforcement for each columns, for each corners. Okay, so you can calculate torsion reinforcement as 3 by 4 ASTX was 595, that is 446.3 mm square is the torsion reinforcement. We will calculate spacing. Spacing is equal to 1000 A5 by AST. AST will be 446.3, A5 will be 5 by 4 8 square. You will get 112 millimeters. So we will round it as 110 mm. Okay, so as this is the reinforcement for torsion. So in our question we will provide 8 mm dia bars at 110 mm center to center spacing at all corners. One more detail, what should be the length? Length should be length of reinforcement. What should be the length? We wouldn't be providing the whole length, right? We'll be providing it as a mesh like this. Right. What should be the length? The length of reinforcement should be 1 by 5 into shorter span, that is Lx. Okay, so that is 4 by 5.8 meters. Okay, so this will be 0.8 meters. This also. Okay, so and this will be given as 4 layers. Okay, there will be a mesh. Mesh means there will be 2 layers, one in this direction and one in this direction. That is 2 layers, and we will be providing it on the top and at the bottom. Okay, so that means 4 layers. That should also be expressed in here. Provide 8 mm diameter bars at 110 mm center to center spacing at all corners as 4 layers. And this should be calculated. Length of reinforcement will be 8 meters. Okay, so that is torsion reinforcement, and this is the design of, if you include this mesh information also in the previous diagram we have just drawn, the diagram is complete. You just have to include these values also, that's it. The statement, and should include this mesh in the diagram, plan diagram at 4 corners, that's it. Then you have completed the restrained 4 edge discontinuous slab 2A slab design. Okay, thank you.